All right. Okay, let's begin. Again, I'm very sorry. I sincerely apologize for missing the class last time. And I've actually prepared a small poll for a supplementary class if anybody would like a supplementary class and what kind of topic they have in mind. So we can take a poll before we finish the class today. And that's that. And so any question from the last time that I talked about self-attention and transformer and the QKV operation? Anything related to transformer at all? I mean, transformers are really important in NLP these days, like natural language processing these days. It is the basis of all the state-of-the-art performing models, especially BERTs and RoBERTs and Alberts and reformers and all those like BERT variants like Electra, GPT-1, GPT-1, GPT-2, GPT-3. All those are based on transformers, like dozens of stacks of transformer actually. So self-attention is probably like the essence of modern NLP. Well, I mean, and everything is modern these days, but still, like the state, like transformer and self-attention is the essence of state-of-the-art NLP models these days. Okay, I guess no question then. All right. All right, let's move on to, okay, so what I was trying to do last time was to draw the connection between transformers or self-attention with graph neural networks, which are essentially the same class, which belong to the same class of functions. So, all right, so this is the let me see if I can, right. Okay, not the black. Okay, cool. So okay, so last time QKV operation, softmax QK transpose divided by square root of D, D being the dimension size of K, was the attention map, and the V was the embedding. So basically we were just weight summing the embeddings, which are basically the tokens or the words in a sentence. So you multiply the first row with the embeddings, and then you get the corresponding first row. You multiply the second row and multiply with the embeddings, and then you get the second row. And the first row was the attention given out from I, the first word, I, to all the other words, including itself. I to like, I to going, I to two, and second row was the attention given out by the second word, which is like. So again, this is like to I, like to itself, like to going, like to two, like to movies, like to end. So that was the essence of self-attention. So attention, the completely fully connected attention arrows or attention like edges, which is why the size of the attention map was n by n. So if you have like 6 words, then it's going to be 6 by 6 matrix. So I'm gonna erase all of this. Now moving on to the graph neural networks, because we want to draw a connection between self-attention or transformer with graph neural nets. So if anybody's already familiar with, like super familiar with graph nets, I guess this would be again kind of a repetitive material. But for anybody else who's never heard of graph neural networks, or who's just grasping the concept of graph neural networks, I hope this is very helpful. So this is the essence of graph neural networks. So H being the embeddings of the nodes, and F being any nonlinear function, D being a degree matrix, and A prime being the adjacency matrix, X being the node embedding, and W being a embedding matrix. So This is a single graph convolution. So given your node information, you apply this operation once, this operation once, and then you get a new embedding of the nodes. So given a node, you get a new set of nodes, and they go through a graph convolutional operation once, and then you can repeat this again. So let me just draw that in detail, actually. Right. So if, for example, let's say that we have a network of papers, right? So how many nodes do we need? Let's say we have 6 nodes. So 1, 2, 3, 4, 5, 6. And let's say, so each node is, let's assume that each node is a paper from PubMed. So it's a biomedical paper. And let's say that this guy in the center is citing other papers like this. So it is citing this paper and this paper and this paper. And let's say, so now we actually need a number. So this is going to be okay. So if we're going to need the number, this is 1, 2, 3, 4, 5, 6. So 3 is citing 1, 2, and 4. 2 is citing let's say 2 is citing 6 and 1. 4 is citing 1 and 5 is citing 3. Also 5 citing I guess this is a bit awkward. Let's say that 6 is citing 2. 5 is citing 2 and 6. 4 is citing 1. And let's say that there is a cycle. So 4 is citing 3 and 3 is citing 4, which is a bit awkward. But let's just, for the sake of argument, let's say that there is a cycle. All right. And let's add another cycle here. 1 is citing 2. Right. Okay, so this is a network. So there are 6 papers in our world, and they are citing each other like this. And of course, each paper has contents. It has like the title and the abstracts and the authors and the introduction, related work, and conclusion and experiments and all that. So that's the given setup. And let's say that we can. So there are 6 nodes, so we can draw adjacency matrix of 6 by 6. So one, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. And 1 is connected. So let's say the rows represent a single node and its citation to other papers. So 1 is connected to 2. All right, so 1 is connected to 2, and 2 is connected to 1. Okay, so 2 is connected to 1, and 3 is connected to 3 is citing. 3 is citing 1, 2, and 4. So 1, 2, and 4. And 4 is citing how many? 1 and 3. So 4 is citing 1 and 3. And 5 is citing 2, 3, 6. 2, 3, 6. And 6 is citing 2, right? Is this correct? Like how many edges are there? 1, 2, 3, 4. Okay, 11 connections. All right. So this is correct. Right. So in the case of a cycle, they form a symmetricity. So 1 is connected to 2, 1 is citing 2, and 2 is citing 1. So 1 is citing 2, and 2 is citing 1. So there's a symmetricity here, but it's not a completely symmetric matrix because there is no, because I'm using a directed edge. So something citing other is a directional relationship. Just because I'm citing some paper, some other paper, it doesn't automatically mean that that paper is citing mine. So it's a unidirectional relationship, right? All right. So, and as I said, this is a paper. So let's say that I want to embed the paper because everything is a vector in deep learning. So just like we learned representations of diagnosis codes or even visits or patients, we can learn a embedding or representation vectors of each paper. And let's say that I'm gonna assume that each paper is, again, I'm going to draw a long rows 6 row. 1, 2, 3, 4, 5. So this is paper 1, this is paper 2, this is paper 3, 4, 5, 6, and they represent the abstracts of paper 1, abstract of paper 1. So let me erase this. All right, so this should be paper 1, 2, 3, 4, 5, 6, and this abstract consists of let's say that the abstracts are just a bag of words. So let's say that this is about the proteins and all, and like such and such and such. So some Medicaid, some Tylenol, second Tylenols, such and such and such. Cancer. This is about human conditions. This is about let's say this is about the medical compounds. This is about hypertension. So these are all just hypothetical assumptions. So what I'm saying is that I'm going to use the abstracts of each paper as a representation of the paper, because I'm not going to use all the the titles, the authors, the related work, the conclusion, experience. I'm not going to exclude all that. I'm just going to take the abstracts of each paper and going to use that to learn the representation vector for each paper, which is typically a lot of people do in biomedical domain. And NLP, I mean, natural language processing for biomedical domain. They crawl thousands or maybe like tens of, maybe hundreds of thousands of PubMed papers from PubMed, the website. And you can easily crawl abstracts of each paper from the PubMed website. So they just crawl the abstracts for each paper and then use that to build a information retrieval machines or information extraction machines, or maybe paper comparison machines, or all that. So in the same manner, I'm going to use abstracts, and so I'm going to use the bag of words approach. So I'm just going to count the number of times each word, like proteins or Tylenols or cancers, how many times each words occur in the abstracts, and I'm going to use them to derive a 128 dimensional vector. So this is one. Well, I mean, this is a bit weird, but this is 128, and this is x. This is 6. So this is paper 1. This is paper 2, 3, 4, 5, 6, 7. So I'm going. Wait, 1, 2, 3, 4. Okay, this is my mistake. All right. So 6 is the end. All right, so 1, 2, 3, 4, 5, 6. So you have the embeddings of each node or each paper, which is the same thing. So now what you want to do in graph neural network is that the essence or the philosophy of graph neural networks is that each embedding or each node is represented by not only by its content, its own content, but it is also determined by its neighbors. So because in the graph neural networks, things are connected in a very specific way. Here, it is connected by this. The connection is dictated by this adjacency matrix A. So I'm going to call this adjacency matrix A, and this A matrix solely determines the connection from the how nodes are connected in our network, and this connection means something. This means that like some papers are citing some other paper, so there's a tight connection between their research. So if we want to correctly or appropriately learn the embeddings of each node or each paper, then we might as well not only depend on its own contents, which is the abstracts, but we want to also consider the abstracts of the papers that each paper is citing or is connected to, because that's how things are related. So for example, here 3, let me change the color. If we want to learn the embeddings of 3, if we want to learn the 128 dimensional embeddings of 3, then its own abstract is of course is the most important information, but the information from 1 and 2 and 4 are also important, because 3 is citing 1, 2, and 4. So that's the essence of graph neural networks, wanting the needs or the desire to consider the neighbors, or not just like one hop. So 1, 2, and 4 are the one hop neighbors of 3, but we can go one step further. So 2 is, let me see. Okay, I guess this is not a great example because 5, like, all right, I'm just gonna add one more line here, just to make things more interesting. So let's say that 4 is connected to 5 as well. So 4 is connected to 5, like this. All right. So as I said, 1, 2, and 4 are one hop neighbors of 3 because they're directly connected to 3. But if we go one step further, then 4 is connected to 5. So 3 is indirectly connected to 5. So like this, like here and here. So maybe we don't want to just consider the one hop neighbors. Maybe we want to use 2 hop neighbors to learn the embeddings of each node. So 3, maybe it is a good idea to consider the abstracts of 5 when we want to learn the embeddings of 3. So that's like going one step further. So I'm gonna discuss how we can do that. All right. So the first thing to do is to actually change a bit, change A to the A prime, which is, I'm going to add, yeah, let's conserve some space, plus I being all right. So I is the identity matrix. So the new matrix would look like this. There's a 1 in all the diagonal elements. 1, 1, 1, 1, 1, 1, 1, 1, 1 here, here. here, 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 here. So this is A prime. And we need another matrix called degree matrix. So is it normalized? Give me just a second. All right, it is normalized. Okay. And another matrix called degree matrix D. Let me see. This inverse. Okay, I see. 3, 4, 5, 1, 2, 3, 4, 5. So the degree matrix is how many connections there are in each row, basically. I mean, it's not exactly the same thing, but the reason that we need degree matrix is we want to normalize the we want to 2 divided by 5. You're right. Inverse matrix. And let me see. So degree matrix being D divided by 1, 2. Let me see. I forgot the detail. Was it a diagonal matrix? A prime times a d prime x w. Right. So it would be 2, 2, 4. Let me see. Is it correct? 2 by 2 by. Okay. I think it was so 2 by 2, 4, 4, 4, 2, and then we do an inverse. So that would be 1 over 2. Right, so okay, I'm going to define the degree matrix as a diagonal matrix. So diagonal matrix being only the diagonal elements are non-zeros and all the others are zeros here. So all the others are zeros here, here. And we count the number of connections or number of citations in each row. So here in the first row, in the A prime first row, I'm going to use color red here. In the first row of A prime, there are 2 connections, the self connection. So now, okay, so before that, before that, the fact that we've added the identity matrix I means that everything has self connections. So now 1 is connected to itself, 4 is connected to itself, 3 is connected to itself. So everything is connected to itself. And we'll see why we need this self connection in the next step when we actually do the graph convolution. All right, so adding the self connection, so every row has 1 extra connection. And because of that, so first row it has 2 connections. So we put number 2 here, and we put number 2 in the first element. And the second row has 2 connections again. So we put number 2 here. Third row has 4 connections. And so we add number 4 here, and so on and so forth. So it's 2, 2, 4, 4, 4, 2. So the degree matrix is 2, 2, 2, 2, 4, 4, 4, 2. All right. So I'm gonna let me erase that. I don't think I'm gonna need that. Let me erase all the embeddings. So okay. Right. So according to the inverse A prime x w. So this is the one step operation of graph convolution. So according to this, so D, what happened here? Okay, I'm sorry. So I'm sorry, something happened to my iPad. Give me 1 minute. Okay, back to normal. All right. So according to this, according to this equation, what we're going to do is we're going to use all these plug-in. We have we have the degree matrix, and we just need we just need the inverse, and we have the A prime, the augmented or adjusted adjacency matrix. XW, I'm going to use the X as the paper the embeddings of the paper representation vector. So we have let me rewrite this. So I'm going to use a smaller version of the matrix. All right, something is definitely wrong with my iPad. All right, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this should be the inverse. So that is 0.5 here. 0.5 here. A quarter, and a half. And the A prime being, there should be a matrix multiplication here. All right, let me erase all this. Let me erase these here. Was 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and 1. Right. And there was the document embedding or the paper embedding, 1 to 3, 4, 5. So this is node number 1, 2, 3, 4, 5, 6. And let's say that I have an extra learnable matrix, a matrix of learnable parameters. I'm just going to write it as W. So this is another embedding matrix that like linearly transforms your paper embedding. So this is 128 by 6. This is 6 by 6. This is 6 by 6. Let's say that this is 121. 128 by maybe. Let's say that we want to maybe transform your paper embeddings into 64 dimensions. So in order to do that, we need the W to be right, something like this. Yeah, I'm very sorry about the size of the matrix. Actually, this is not the most ideal. So this should be 128 here, and this should be 64 in W. So then you can get like 6 by 64 dimensional vector after this. But all right, okay, it's just for the clarity. Let's just erase this and use this as a W. Right. So what happens when you do this operation? So okay, so there should be f here, f of course. So f is a nonlinear transformation function, or f is a nonlinear function. So it could be like a feed-forward neural network with nonlinear activation. It could be multiple layers of feed-forward network. It could be anything. But basically, it is something that is just nonlinearly transforms the outcome of this D inverse A prime X and W here. So what happens? So I'm gonna call XW as just V. So so I'm gonna call this as a V. So this just some vertex or some embedding, some node embedding, some new node embeddings actually, because X was the original embedding and W is the new embedding matrix. So V is a new node embeddings. And then let's say that you multiply the first row here. So first row being you multiply the inverse here. And the inverse, wait a second. Okay, so something was definitely wrong with my degree matrix. D inverse. Or maybe not. Let me see. 1, 3, 4, 2, 1. So let's see. 1, 1. Right, and then 4, 4. Let me see. Okay, sorry about this. So the end product of D inverse A prime should not be like this. Let me see. So what should really happen here is that we need the a row by row multiplication. So let me see. So let me how to draw this more succinctly. So it's not a matrix. It's basically it's 1/2 times this, 1/2 times this, 1/4 times this, again 1/4 times this, 1/4 times this, and 1/2 times this. So this becomes your a single vector actually. All right, there should be a nicer way to convert this into a matrix format, matrical format, but I'm just going to use it. So the essence, the philosophy, the objective is to actually normalize the adjacency A prime matrix, the augmented or the adjusted adjacency matrix, because if there are more connections in some row than the other, then if you multiply that then it's gonna like blow up your. Basically, the scale is not gonna match between different rows, but which is not always a good thing. But we'll get to that a bit later. So, the basic format of graph convolution is that you need to normalize each row of the adjacency matrix. So since there are two connections here, this becomes 0.5. So if you multiply 1/2 to this row here, then it becomes 0.5, 0.5. So it becomes 0.5, 0.5 here, again 0.5, 0.5 here, 0.25, 0.25, 0.25, 0.25, again. So that's the whole spirit of multiplying the degree of to inverse of the degree to your adjacency matrix, the A prime, the adjusted adjacency matrix. So let's say that you've already did that. Let's say that so the first row is 0.5, 0.5, second row is 0.5, 0.5, and so on and so forth. So what happens when you multiply the A prime? I'm going to call this the inverse A prime. So let's just forget about this one. So 0.25, 0.25, 0.25, 0.25 here. 0.5 here, 0.5 here. Right. So this is your D inverse A prime matrix of 6 by 6. And you have the V embeddings, which is the newly embedded. All right. So basically you're multiplying, you're doing a matrix multiplication of D inverse A prime with the V here, like this. So what happens when you do this? What happens? Then when you multiply this row, I'm going to use color red here. When you multiply this row with this, all right, okay, just for the sake of the argument, let's say I'm gonna erase all this, and you have a new embedding named V. So this is V. This is V. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So when you multiply the first row of D inverse A prime with the entire the new embeddings V, then what happens is you get. All right, I'm gonna ignore the nonlinear function for a minute. let's just see what happens. So when you multiply the first row with the v, then you get 0. The new embedding is 0.5 times v1 plus 0.5 times v2. That is your first row. So we're gonna have 6 rows. Second row is 0.5 v1 plus 0.5 v2. It's the same thing. And then third row is a bit different. So 0.25 times v1 plus 0.25 times v2, 0.25 times v3 plus 0.25 times v4, so on and so forth. So the last row is going to be 0.5 times v2 plus 0.5 times v6. So what happened here in the when you multiply d inverse a prime with the v embed, the new embedding v, then what, and then you derive so this is d inverse a prime xw or v. What happens is the new embedding of the new embedding, or the newly derived embedding of the first node is actually not, it is a combination of itself. So I'm gonna go back to the, actually I should have used the blue color here. So it's a combination of itself. So half of itself v1, because v1 was originally itself. So half of v1 plus half of v2. So that becomes your new embedding for the first node. And that's what happened is, since it is connected to, if you look at the graph here, 1 is connected to itself and 2. So it is citing itself, and self-citation is not really, you never cite your own paper in actual reality, but because we added the identity matrix I, so there's always a self loop. So the node 1 is connected to itself and 2. So that is why the new embedding of 1, the node number 1, is half of itself and half of number 2, node number 2. And if you move to the third row here, the new node embedding for the node number 3 is a quarter of itself. So 0.25 times itself, which is here, a quarter of itself, plus a quarter from its connections, which is 1, 2, and 4. Because 3 was citing 1, 2, and paper 1, and paper 2, and paper 4. So the new embeddings for paper number 3 is a bit of itself and all its neighbors. And we do this again and again until the last node. And the last node being node number 6, which is connected to itself, which is connected to itself and 2. So it is citing number 2. So that is why the last node is the new embeddings for the node number 6 is a bit of itself and a bit of its neighbor, the v2. So you get the idea. So you do this, and then you multiply, and then you apply a nonlinear transformation f, which is to add more expressivity or capacity to your model. So if you just do d inverse a prime xw, then all you're doing is just linearly transforming your embeddings. But the power of deep learning comes from non-linearly transforming your latent representations, like tens of times or hundreds of times or thousands of times. So you always need a nonlinear activation somewhere. So you put f here, which is the nonlinear transformation factor in your graph convolution, right? So now you see why we've added the identity matrix I here, because without this, then when you do a graph convolution operation, then you are losing your information. You're losing yourself when you're doing when you're just simply gathering information from your neighbors, and you're not retaining your information from yourself. So which is not what we want, of course. We want the embeddings to still contain some information from itself. For example, like if we didn't put the identity matrix I, then this part here, the new embeddings for V1, the node 1, would only consist of V2 here, and there would be no V1. So it wouldn't be like a bit of information from itself and a bit of information from the neighbors. It'll be only information from its neighbors without your information retained. So that is why you need to add the identity matrix. Right, okay. So far pretty now it's pretty intuitive, the whole like D inverse A prime XW. This is I mean there's a pretty like heavy mathematical justification for why this is a good idea. Like there's like spectral analysis and all that related to adjacency matrix and all that, and like graph theory, but which is not the focus of this course. The important thing is that this graph neural network is now become a whole family of functions. It's not just GCN is not the only graph neural networks out there. So now graph neural networks is any neural network function that operates on graphs using or based on adjacency matrices. So, and the intuition behind it is pretty simple. You just want to do this here. You just want to do this. Right, okay, so this was a one step of operation. Let's see what happens when you do another time. So all right, we're running out of space. All right. Okay, I'm gonna have to erase all of this. I'm gonna erase this. Erase all these. Erase this. Erase this. I'm gonna copy. All right, so I'm going to copy the red matrix here to this part. It was 0.5 V1 plus 0.5 V2. Not exactly, sorry. Not exactly. F function of 0.5 V1 plus 0.5 V2. Second row being F of 0.5 V1 plus 0.5 V2. Third row being F of 0.25 V1 plus 0.25 V2, like this, and the last row being F of 0.5 V2 plus 0.5 V6. All right. Okay, now I can erase all this. And of course, there is a W here and another F. All right, so what's happened here? It's now this becomes, so we've done a single graph convolution operation, and we've derived this H here. So let's say that I'm gonna need H2, H1. So H1 being the output of a single graph convolution operation, and you know that the contents of each node or each row of H1 is is simply just a 0.5 v1 plus 0.5 v2 applied and f the nonlinear transformation function f applied to the embeddings. So you can this is pretty straightforward, H1. And now we're gonna repeat the process again one more time. So we're gonna do a 2 graph convolutional operations in total. And of course, this W will be actually a new W. So this is a new W2. So the W will be a new embedding matrix, but D inverse A prime will stay the same. This is always the same because your graph network, the structure of your network doesn't change. So D inverse A prime stays still. H1 and W2 is the new contents. But when you do this, again, I'm gonna assume that I'm just gonna assume that F is here. And I'm gonna treat H1 W2 as a V2. And your new embeddings would be, all right, so what happens here is it's 0.5, so the new embeddings for your first node is 0.5 F, 0.5 V1 plus 0.5 V2 plus 0.5 F, 0.5 V1 plus V2. All right, so basically it's basically you multiply half here, you multiply half here, and you multiply half here, and then you add them together, and that's how you get the first row. So not much has changed because this new contents, the contents of your new row, the first row of your new matrix here, the new matrix here is still drawing information from node 1 and node 2 only. So it only consists of node 1 and node 2 only, and there are some nonlinear transformations, some like put here and here, but basically everything about the first row is still, it's about a combination of information from V1 and V2. I mean node 1 and node 2. So nothing much has changed. Let's see let's go to a bit more interesting case. So third row, so second row is still the same. Second row is still the same. You multiply this row with this column, with this matrix. So it's still, the second row is the same as the first row. So nothing really changes. Third row is way more complicated than the first and second row. So third row, what is it? So third row is 0.25 times this guy, 0.25 times this guy, 0.25 times itself, 0.25 times another potential row here. So what's happened here? So it's 0.25 times, I'm gonna just write this as V21 plus 0.25 V22 plus 0.25 V23 and 0. All right, I don't have enough space. Anyway, you get the idea. So what's happened here? So the new node is the new embeddings for the third row or the third node is coming from it should come from actually. So yeah, I actually needed another. So 0.25. All right, I'm going to write this here. 0.25 times V24, right? The fourth row. So 0.25 V24, right? So and there actually should have been 0.25 V3 plus 0.25 right, 0.25 V4, right? So until you've all right, sorry, this is a bit cluttered. 0.4 0.25, 0.25 V1, 0.25 V3 plus 0.25 V4 plus 0.25 V5. All right, now, okay, now we're all done. So the new, right here, the new embedding for the third row, where the node number 3 is coming from V1, V2, V1 and V2, which is V1 and V2 here, which consists of only the first node and the second node information, because it is coming from because V1 and V2 is all about V1 and like V superscript 2 subscript 1 and V superscript 2 V superscript subscript 1. It's all about node number 1, node number 2. So nothing new comes from this. Then V superscript 2 subscript 3, it's all about V1, V2, V3, and V4. And it was already so this third element, it doesn't add new information because it is just retaining itself. So it is pulling information from itself 0.25 times and then pulling information from V2 V22, and so just it is another self loop. So the new information, the only new information comes from this element here, which is a 0.25 times V4, and V24 contains V1, V3, V4, and V5. So the only new addition is V5 here, the V5 element here. And this is possible because, so what happened here is because we are going 2 hops. This was the first hop, H1 was the first hop. We're doing a second hop here in this entire process. So this becomes your H2, the new embeddings. I mean, of course, including the F. This becomes H2, and H2 is now, it is, so doing two graph convolution enables you to learn embeddings based on neighbors 2 hops away from yourself, and that is shown here by that the third row or the third node is now finally drawing information from V5 here. So it was first jump. So these are the one, as I said, 1, 2, and 4 are 1 hop neighbors, and 5 is a 2 hop neighbor, 1 and 2. So 2 hop neighbors. So once you've done 2 graph convolutions, now you're drawing information from your 2 hop neighbors. And if you go one more time, what would happen? So if you go one more time, then 5 is connected to 3, 2, and 6. So in 3's perspective, in node 3's perspective, 1, 2, and 4 are 1 hop neighbors. 5 is a 2 hop neighbor. Then 2 and 6 are, 2 was a 1 hop neighbor, so it's like a 1 hop neighbor and third hop neighbor still. But 6 is a third hop neighbor only. So 1, 2, and 3. So 6 is a third hop neighbor. So if you apply graph convolutions 3 times, then embedding for node number 3 will now draw information from node 6 as well. So you can do this as many times as you want. You can do like 3 convolution, 4 convolution, 5 convolution. Like you can do as many graph convolution operations as you want, as you need. So there is no like set number, like a fixed number of graph convolutions that you must do or you must not do. So basically, okay. So this is the essence of graph convolutional neural networks, and there are certain subtle variations as to like how you define your F network, how you define your feed-forward neural network, whether you use skip connections before and after your graph convolutions, or how you do, like, whether you use degree matrix or not, or there are a lot of variations, but basically, okay, my iPad is a bit, give me a second. All right, this is not making me happy. All right, anyway. All right, anyway, so as I said, there are a lot, all right, I hope I can erase all of this, all right? All right, so there are how many components here? There's F, D, A, X, and W, and you can use, this is just a framework. So a graph neural network is just a framework. So F can, like a very simple variation is your H can be F plus D inverse A times XW plus, so this H, all right, I'm sorry. H1, so I'm not going to, okay, I'm going to use HK instead. HK, WK, and this becomes, as I said, because you can do graph convolutions as many times as you want. So let's say that you're doing like K plus 1 times or whatever. So K plus 1. And a simple variation is you can just add HK here again. So what does this mean? This is just a skip connection or residual connection, just like ResNet. So before and after you do graph convolution, you just simply add the original node embedding, so that you just lessen the burden for the graph convolutions. Like if you need graph convolution, then a lot of weights will be put in here. If not, then a lot of weights will be put in here, something like that. Anyway, so again, this was a very, very, very simple variation of graph nets. And of course, as I said, you can use like a very, very deep network for F. Like F can be just a single neural network with a single hidden layer, or 2 hidden layers, or 3 hidden layers, or whatever. And again, of course, as I said, you can use the degree matrix or not. There's pros and cons. Like if you use degree matrix, then your whole graph convolution operations become stable because you're normalizing your A prime matrix. But if you do that, you are losing certain information, because if you just normalize everything, then what's the point of having a lot of connections to begin with? It's because like the scalar value of your embeddings would indicate that your node was heavily connected to a lot of things. And if your scalar value for a certain node is small, then it means that your node was not connected to a lot of things. So there are trade-offs. And if you're interested in the further discussion, there's a paper called like how powerful are graph nets, which was, I think it was presented in iClear 2019 or iClear 2018 or something, I forgot. Anyway, so that, yeah. Anyway, there are a lot of variations, and even you can even add attentions for your adjacency matrix, and that's called graph attention nets, which is pretty similar to which is also like drawing connections between self-attention and graph nets. So since we have 20 minutes, so let me just very briefly go over that. All right. So, okay, so any questions so far with graph nets? I hope that everybody can confidently implement their own graph nets, and if needs arises, if the attendees are dealing with structured graph data sets or graph structured data sets, they can just simply implement graph nets with PyTorch and apply this, and then get the new embeddings and such. Oh, the important thing is, so far I've only discussed how to derive new embeddings or derive embeddings for each node in your graph. But sometimes you want to derive the embeddings for the entire network, entire graph. So so this equation will only get you the embeddings for individual nodes, but sometimes you want to derive the embeddings for entire network. So in that case, you can simply add a dummy network called V with, I'm sorry. You can just add a dummy network called let's say G, which represents just the graph, and let's say that it is connected to every single node in your graph like this, and then of course it is self-connected. So if you add this if you add this placeholder node G, which is connected to all the each and every node in your graph, then that becomes your graph representation. If you learn the embeddings for G, then you can use G as your graph representation. Or simply you can just take the HKs, and just add everything, like, because HK would be like, there would be the same number of embeddings as the number of your nodes, and you can just simply add everyththing, and then, or you can just average everything, and then you get a single embeddings here, and that becomes your graph embeddings or graph representation vector. I mean, there's just one like ground truth way for deriving your graph representation vector. Anyway, that's another story. Sometimes you want to like classify the entire graph, like, given this graph, what does it look like, and given this another structured graph, what does that look like, something like that. So in that case, you need a fixed size vector to represent your entire graph. All right, no questions so far? All right, cool then. All right, I'm gonna clear everything, and then I'm gonna move to the connection between graph nets and self-attention. All right, finally. All right, so let's just look at the slides. So this is all right. I'm gonna try to use both my iPad and the computer at the same time. So as I said, so self-attention, I mean self-attention, the attention map of self-attention is this matrix here. And it is a normalized attention map given from each node to all the other nodes. And that's why it has an n by n matrix. And softmax QKT transpose D is the, all right, my iPad is causing me a lot of trouble. All right, I'm sorry, give me just a second. Right, like this. And then it has embeddings, and then you get the attention, you do the QKV operation, attention QKV. And then that is basically a weighted sum of the nodes or the tokens, weighted by the attention strength, like exactly like this. And if you go to the graph nets, it's exactly the same thing. Attention map is now just adjacency matrix, or it's a normalized adjacency matrix. We multiply the degree matrix with the adjusted adjacency matrix A prime. So it has 0.5, 0.5, 0.333, and such and such. So it is a convex weight. Each row sums to 1. Each row sums to 1, 1, 1, and you have the embeddings for each node. And before you had the embeddings for each token, you have the node embeddings for each node, and then you multiply, and then you get D inverse A prime X W, and you just need to add the F function here, right? That becomes your graph convolution. So before you add the F, the inside is simply just weighted sum of your node embeddings. So weighted sum of your node embeddings here and here and here. So you can see a clear connection between this and this. It's exactly the same, actually. I'm going to erase this. Right. So GraphNet has, well, okay, so here I'm using C instead of H. So C instead of H, but that's the only, and instead of F, I'm going to use MLP, multi-layer perceptron, which is basically just a nonlinear transformation function. Transformer has a function that looks like this. So this is a new context embedding for your words or your tokens. And this is a QKV operation inside. And what transformer looks like is there's a self-attention block here, and then there's a multi-layer perceptron block here, and then there's some layer normalization and skip connections like here and here, and here and here and something. And this becomes your transformer block. So inside the transformer block, there's self-attention block here, and there's MLP block here. So this is MLP, self-attention. And if you break down your context vector, then the Q and K and V would look like this. So Q here, K here, V here, and V is, right, just erasing everything again. V here is C, the previous embedding, plus your embedding matrix, which is exactly like this. Cj minus 1 times Wj and Cj minus 1 times Wj. So there's exactly a one-to-one mapping. So do I have embedding? Yeah, I have the, right, I have the mapping. I have the one-to-one correspondence. So the adjacency matrix and self-attention are the same thing. One is just purely data-driven. So self-attention is purely data-driven. Adjacency matrix is purely prior knowledge-based because you already know the structure of your graph. You move on to the node embeddings and token embeddings. It's exactly the same thing. And that's how you can assume that, I'm going to erase this. You can, this is why you can be motivated such that maybe you can guide your transformer or your self-attention operation so that it can learn meaningful graphical structure of whatever. In my case, I'm a healthcare guy, so I'm looking at the electronic health record where a patient makes a visit, and inside a visit, he or she, the patient, was given diagnosis 1 and 2. And for diagnosis 1, the patient was given some medication and some procedure, and that procedure led to 2 lab values. So in this case, this is a pretty straightforward a graphical structure. And hopefully you want to, so if you know the ground truth structure, then you can represent your structure as a adjacency matrix here like this. There is 1, 2, 3, 4, 5, 6, 7 nodes, including the visit node. And notice that this is a symmetric matrix. Okay, I forgot to mention the symmetric matrix part. So I'm sorry about that. All right. So before in the citation network, everything was directional. So it was a unidirectional edge or unidirectional relationship. So it wasn't fully symmetric, but you can make your networks fully symmetric whenever you want. It actually helps your network learn a better embedding for each node because it is bidirectional, because you are sending signals both ways. So if you make your matrix symmetric like this, here, even though implicitly even though there is implicitly a direction in your graphical structure, just forcing it to have a bidirectional relationship makes the learning process a bit easier or smoother. So it's always a good idea to make your matrix bidirectional, unless you have a very specific reason why not to. Anyway, so as I said, because there's a one-to-one correspondence between graphness and transformer, if you don't know the true structure like this, let's say that you don't know the structure of your visit, but hopefully if you guide your transformer well enough, then your self-attention might look like this. Well, not exactly like this, but hopefully something similar to this. And the way you do it is you can add some prior knowledge such that you can use conditional probabilities for every single pair of your codes or your tokens, actually. So for example, you don't know the structure of your visit, but you do know that there are 1, 2, 3, 4, 5, 6, 7, 8 nodes here in your visit. Then you can calculate conditional probabilities, like given chest pain, what is the probability of seeing EKG in your visit? And given benzonatate, what is the probability of seeing QRS lab values in your visit? So because you have a lot of like millions of visit records in your EHR, you can count the number of, you can count P EKG, you can count the P QRS. Like basically you can calculate the simply just occurrence probability for each code. And then based on this, you can calculate P EKG given P QRS conditional probability, because you already have the training data for which consists of the visit records. So you can calculate the conditional probabilities, and then you can inject this conditional probability in your self-attention map, so like here and here, like corresponding cells in your in your self-attention map, and then you can start from there as a prior knowledge. So it's a bit of like a regularization factor. Anyway, I won't go into detail because this is this technique is just too focused on my paper. But important thing is there's a clear connection. There's a strong connection between self-attention and transformers. And a paper named Graph Attention Net has drawn from that intuition even before I did, and got a lot of good reviews, and a lot of people are using Graph Attention Net these days. So it's worth taking a look. Okay, I won't go into any more details in this particular EHR domain, right? So if there is no more question, I'd like to do the poll, as I said, about the supplementary class. So in my original plan, I was going to use my next class as a Q&A session before you do the project presentation in the next week. So we are missing, but since I missed the last class, we can use an extra class if you want to talk about potentially a couple. I have a couple of candidate topics actually, so that's also part of a poll. Right? So give me just a second, I'll just direct you to the poll.